more algebraic way? Well, we all know that somehow the point is that this image can be infinite. Like the usual way of studying representation of finite group doesn't quite apply. Why is it infinite? Well, let's look at the sort of the list of Galois group over here. So the Weyl inertia is a pro-P group. So this P is different from L. So this topology doesn't quite sort of work together. So somehow from that you can probably guess that the image of the Weyl inertia inside of there is finite. That we're going to show in a minute. And then what's sort of the trouble? The trouble term is somehow this middle piece here, the time inertia. The time inertia inside of this sort of z hat away from this sort of pro completion of z here. There's a factor which is ZL. That's the part that could have infinite image in here. And this sort of this unramified part, of course it can have infinite image as well, but then after all it's just sort of generated by the one element. So it's a little bit, I guess it's not that sort of serious an issue. So the goal of Gaussian local monodromy theorem is to sort of resolve the issue of sort of the time inertia, where this sort of ZL here. Look at how ZL acts on this under this representation. So step one. So let me just sort of give a kind of a quick sketch of the proof of the Gaussian local monodromy theorem from sort of step-by-step thing. I'll get to the end and then state it. So the image of so first of all, look at the Weyl inertia. This is a pro-P group. The first claim that this is always finite. So quick proof. So let's consider rho. It's restricted to the Weyl inertia. Goes from Y inertia to GL and OL. Okay? And I want to maybe look at the, how should I do this? So maybe look at the sort of composition of reduction mod bar pi of L. So this is reduction mod bar pi of L. Okay? So let me call this one rho bar restriction to PK. Okay? Good? Okay. Then, how should I do this? I thought about this, how I'm going to explain this, but so maybe we look at the sort of reduction here. The kernel of this reduction is 1 plus var pi L times matrix, right? So that's all the matrices modulo var pi L congruent to the identity matrix. So what I want to claim is that somehow the image of rho restricted, or maybe just write rho pk. Yeah, I don't need the reduction. Anyways, let's look at the sort of image of this Weyl inertia inside GL and OL. So this is, because pk is a pro-P group, so this is a pro-P. And if I want to look at sort of the kernel of this reduction, L is a finite extension of QL. So therefore, this is a pro-L group. So you have a pro-P group. Look at the intersection with another pro-L group. If you sort of model out any sort of open compact subgroup of this, this side is going to be a P group. This side is going to be an L group. So they have no intersection. So that means that somehow, like the image in here has no intersection with the kernel we have over here. So therefore, we see that the rho of pk is the same as rho bar of pk. Namely, the image of pk inside here is the same as the image of sort of having this image project down to the residue representation. And therefore, because this is a KL is a finite extension of FL, so therefore it's just finding many elements in here. So this is finite. One thing I want to say is that somehow we didn't just prove this is finite. We also showed that if you want to understand the ramification of the Weyl inertia, it's enough to look at modulo var pi L. That tells you everything about the ramification. So first of all, understand, I guess, the well inertia of this. Let me still keep this picture here. So let me write this is z away from 1. This is z hat. Okay. Write it over here. Step 2. So a corollary of this is that I can always find an extension, find a Galois extension. Let me call it k double prime of k, because eventually I want to get to k prime. So let's start with the double prime and come back, such that rho of the well inertia subgroup of double prime is trivial. Okay, so I go up to sort of some extension so that this image becomes trivial. Get to a subgroup of this. So once we're at this stage, now get to the second step. Let's just say that I look at rho. I want to look at, maybe just sort of do it more directly. So I want to look at sort of the Galois group of this k double prime, so sort of find an extension of k. And this will be mapping trivially. So the well inertia will be trivial. So so this will map factor through the gk double prime over the well inertia k double prime. So namely this part is sort of gone. So I just look at sort of bottom part, 2 parts of this. So this is isomorphic to, as we see. So I guess this is so this z hat will act on this one. So this. So it's a semi-direct product of the arranged part, semi-direct product with the k inertia, and this goes to GL and OL. Okay. So inside these 2 groups, we have 2. Okay, this is sort of v k double prime, and this one I'm going to call sigma. Did I use sigma? Oh, I used tau. It works. Okay. So you can think of this as this is a geometric Frobenius, as we discussed. And this bit here, this is a generator of time inertia. Because this is a pro-cyclic group, so you can pick the generator that corresponds to 1 here. And this phi would serve. Let me just write phi. If I use phi conjugation on this tau, how do I do this? Maybe I'll deliberately write conjugation the wrong way. Okay, so this is sort of going to be q k double prime times. Oh, sorry. Okay, tau k double prime to the q k double prime. Okay, I deliberately note here that my phi is geometric Frobenius, so I deliberately write the conjugation the wrong way. So -1 is here. Then I have this tau k double prime to the q k double prime power. Otherwise, I would have 1 over that. Anyways. So step 3. So this is rather explicit after a finite extension. So the goal is that somehow we kind of go to a finite extension and make things very explicit, and then want to reinterpret the action of this time inertia in a slightly different way. Oh, sorry. Step 3. I want to show that I can find a finite Galois extension such that rho of the entire inertia subgroup is, or maybe R, well, are unipotent, i.e. all the eigenvalues of the element in this image are just 1. Okay? So I want to make another extension so that all the eigenvalues, all the matrices are conjugated to something like this. Okay? Therefore, if you minus 1, if you raise to, say, nth power, this matrix will become that 0 matrix. So that's unipotent. So how do I do this? Okay, well, I already made a finite extension, right? So inertia subgroup now, essentially, we just need to look at, basically just look at this tau action, right? I don't have to worry about other things. So my claim is that, okay, I need to show that after further extension, the time generator will act on this sort of n-dimensional space by a matrix like this. Namely, all the eigenvalues are 1. To do that, essentially I need to show that all eigenvalues now of this tau k double prime are roots of unities. Just means roots of unity. Right? Maybe I need 2 lines here. If I do this, I can, after replacing k prime by a finite extension, leave 2 lines. I can say k prime. I can assume that my time generator is the original time generator to some sort of big N power, where somehow you have sort of finite many roots of unity. You can find a big N such that raising to nth power, this root of unity will become 1, and therefore the row of tau k prime will look like that. So this is sort of an eigenvalue game, in the sense that if you make sure that your tau k double prime, the eigenvalues of this are all roots of unities, then raising to a large enough power, they will become 1. But if there are arbitrary sort of elements in L or in QL, say, you can raise to any power you want, but you won't get to 1. So this point is to show these eigenvalues are roots of unity. So let's do this. Why are they roots of unities? I'm going to use this equality here. Let me call it star, maybe. Okay? So note that if I have this tau k prime here, if I conjugate it by another matrix, right, the geometry for Venus, it will raise its tau to the qk power, qk prime's power. Questions? Okay, good. So by star, we see that, well, if I consider the set of all the eigenvalues of tau k double prime, that's a set of sort of some numbers in Q alpha r, say, and but we know that if you conjugate the matrix, the set of eigenvalues will not change. It will just basically somehow permute these eigenvalues in some sense. So this would be the same as eigenvalues of tau k prime, and raising these to the q to the k double prime. So, sorry, maybe I should, what k double prime is the number of elements in the residue field of k double prime. Okay? So I have a bunch of numbers, and that's the same, that's the same set of these numbers raising to q to the k double prime power. If you think about that. And this is a finite set. And how could that be possible? I guess the only possibility is that they are somehow, I guess they're roots of unities, in the sense that somehow, like, if you start with an element alpha here, right? And over here, correspondingly, I guess maybe just sort of do a heuristic argument. If you want the eigenvalue is alpha, then by this equality, then alpha to the q to the k double prime is an eigenvalue. And you do the same argument for this one, you see that alpha to the q to the double prime square is another eigenvalue. And you continue on. But this is a finite set. So this thing must end at some point. That means that this alpha must be equal to q to the sum r, q to the q k double prime to the sum r power. That must be equal to r, to show alpha at that point. So that means alpha is what q to the r is q to the r minus the first root of unity. Right. So this is finite set, so that means it's all eigenvalues of tau k r root of unities. So basically, it's somehow raising to q. Let's ignore this. It's raising to q's power, meaning just basically to permute these eigenvalues in some ways. So Gorsanik's idea, I think of all the argument, I think this is the most, it's not trivial. It's not that difficult to, once you know you want to go this way, it's not that difficult to prove, but somehow this is an interesting observation. Somehow, it's some technique that actually shows something not so trivial. Anyways, so a corollary is that the Gorsanik realized that somehow, when you have a unipotent matrix, sometimes it's better just use the log of that to represent it, which is for more algebraic. So let me sort of state it in a more direct way. So there exists a endomorphism of the endomorphism. So V is sort of L to the nth power, the representation you have. This matrix is nilpotent. So this matrix will be the log of this and tau that. There exists a unique such matrices, and there exists a finite extension such that for every sigma in the initial subgroup of this k prime, this rho sigma is equal to the exponential of TCL of sigma times n. Well, it's not finished yet. Let me move to the other side and write it out. Maybe just write here what this n is. So what is n? Oh, sorry. I shouldn't use c. So let me change it to tau because I've been using tau. Okay. So first of all, by the discussion above, what is this n? So this n is, well, I can sort of take my tau to be tau k prime. That's to say that this is sort of the topological generator of this thing. Namely, I want to take my tau, maybe I should write it here. So I take a tau k double prime. Tau k prime, so that, but that's, I think, right. That's a little bit annoying. Sorry. This is TCL. Let me write it over here. Sorry, this part I didn't prepare well. Right. So how do I get that? So let's see. So I'll have to okay, and then somehow inside of this, I have a T prime K. K prime are ramified. Okay? And supposedly there's a T prime of theta L. So this extension here, so this is multiplication by somehow the ramification degree of E prime over K, the 10 part. Okay? So we started with the top one. Now we pass to a finite extension. But somehow the corresponding tame map is slightly off by how much sort of the tame extension, the tame ramification degree. That this E basically corresponds to this expression over here. Namely, somehow we started with some sort of tau k, but now we're raising to tau k's power. So therefore, let's see. So therefore, if I how should I put this? So maybe I start with this one here. So correspondingly, I have this sort of tau k prime here. Okay, and under this TL, this will go to the number tamely ramified k prime over k. Okay, so now I wanna take k. I want to take n to be log of rho of tau k prime. But then I have to divide it by this normalizing factor, 1 over e to the k prime over k 10. And that's my n. Sorry, this is a small subtlety here because my t zeta L is normalized with respect to k, but not. But when I do this, I really want to just use tau k prime for that. But somehow we'll have to sort of renormalize these two things. They're off by a tamely ramified index here. So that's what this n is. Essentially, I'm taking the log of this. By log, I mean the sort of formal log in the sense of sort of 1. I'm a little nervous. Rho tau k prime minus 1, and then minus half of this thing squared. But we know that this is unipotent. So if I minus 1, it's going to be a sort of minus 1 is going to be a nilpotent matrix. If I raise to nth power, it will be 0. So this is not an infinite sort of sum, just sort of finite sum. Right. So this is what this log means. So this exponential is also sort of the same thing. You just write 1 plus this matrix plus this matrix squared over 2 and so on and so forth. Okay. Once again, because this n is unipotent somehow. I'm sorry. This n is nilpotent, so therefore this is just basically a finite sum. Okay. Sorry about this. Maybe I should have done this in a better way. But anyhow, so that's what this n is. So this n is essentially the logarithmic of this unipotent matrix. And because of this property star here, this n enjoys the following property that if, moreover, this if phi tilde k is a lift of Frobenius to the Gauss group of k, then rho somehow this equality will translate to here. Maybe just again sort of put minus here. That's equal to qk times n. In the sense that somehow over here, this is sort of written multiplicatively. Whereas when you translate over here, you're taking sort of log of this, it will become sort of additive. So in some sense, what's happening here is that we're translating just a little part of the sort of tame part of the action on the space via a nilpotent operator and not changing everything else. So the upshot is that I want to describe the representation rho more algebraically. And hopefully independent of L. So that's the upshot. In the sense that somehow we look at this sort of Galois group here, right? There's a Frobenius part which we can't do much about. In fact, we'll see later. And this tame part, for different prime L, we consider L-adic representations. But somehow, later we'll say a little bit about what Langland's program will predict. But somehow, presumably, L-adic representations for one L will be not too much different from L-adic representation for a different L. So this Grothendieck's local monodromy theorem basically gives a way to extract out certain ambiguity of the L inside of here, to make it more algebraic so that you can compare this different L-adic representation for one L with the L-adic representation for a different L. So that's where we're going for. The next board. As I said, somehow we can't do much about this one, so let's introduce so-called Wade-Dillinger group. It's a Wade group. So the Wade group is, remember that we have this exact sequence of initial subgroup, a Galois group, and sort of this identified part. Now I want to consider the subgroup generated by the Frobenius. So this one here corresponds to Frobenius. Now I can pull back this, or maybe just take the pre-image. I'll maybe give a name. This is not standard. So I get this to be the side inverse of. I want to discretize the Frobenius. In other topologically wise, this is still a profinite group, but somehow I want this Frobenius to be somewhat discrete. I don't require somehow power of Frobenius will kind of converge to one anymore. So the Frobenius are kind of free. So theorem. Let's just rephrase what we just did in some sense, with a little bit more. Grothendieck's monodromy theorem. I want to fix an isomorphism. Delta from C is the algebra closure of Q. That's okay. I want to fix it once again, because C as above, zeta as above, the roots of unities. I want to fix a lift of Frobenius, feature decay of V in the Wade group. Then there's a equals category. Which somehow slightly unfortunate, but it depends on the data I have over here, delta, C, and tutor phi k. But somehow the dependence is not that bad in the sense that for another choice, there's a natural way to, natural sort of way to transfer one equivalence to another. On the left-hand side, I have rho k. On the right-hand side, this is called a Wade-Deligne representation. We'll write that in a bit. This is continuous. On the right-hand side, it consists of two things. One is a continuous representation. The other one is a so-called monodromy operator, such that R of an element G, if I conjugate the monodromy operator M by this G, then I get QK, or Q maybe, Q to the minus psi of G times it. So the Gaussian monodromy theorems gives equivalence of the following two things. On the left-hand side, I have a so-called allied representation of the Wade group. Maybe just sort of say that if I have a representation of the Galois group, allied representation of the Galois group, allied, I can definitely get, by restriction, get a representation of the Wade group. The difference is that over here, somehow I need rho k of the Frobenius to be topologically nilpotent. Topologically unipotent. Or maybe to some when n is divisible, sufficiently divisible. So when n is sufficiently divisible, for Galois representation, I need the rho k of Frobenius to some power to be topologically well, I don't need topology, just to be unipotent. In the sense that because in this Galois group, the Frobenius is z hat. The Frobenius part is z hat, so a power of Frobenius will be close enough to 1. So therefore, I want the Frobenius to be, so some power of Frobenius to have sort of all the eigenvalues 1. I'm sorry, so topologically, unipotent. Like that. I mean, I want things to converge on the Frobenius direction. Whereas over here, if you consider Wade representation of Wade group, the Frobenius doesn't have to sort of converge, because if you're raising Frobenius to nth power, it would just sort of go along inside of this z. You don't have any sort of you don't have to require any sort of convergence condition. So that's the only subtle difference between the Galois representation of the Galois group and the representation of the Wade group. So you have no constraint on the Frobenius being sort of topologically unipotent. And going from here to here, basically you see that on this side is a continuous representation where the coefficient field is QL. On the right hand side, the coefficient is taken to be C, in the sense that going from here to here, I removed the dependence on L, on the prime L. The reason for such sort of such construction is that somehow it goes a little bit beyond somehow, or we're going to talk about this course, but somehow you probably have heard of this. When we talk about sort of étale cohomology of a variety, you can talk about the L-adic coefficients for any prime L. But at the end of the day, all these L's, so all this information for different L's will be related. The way they're related is that when you translate all the information through this isomorphism, over here, when the coefficient becomes C, they become the same. So somehow the Grothendieck's local monotopic theorem gives a way to compare L-like representations for different L's. Okay, so over here, this is called the Wei-Deligne representation. It has two parts. So first part is just a representation of the Wei group, a continued representation of Wei group with coefficients in C. Another part, it has a monodromy operator N, which will come from this, the action of the tame inertia here. And somehow this specifies sort of the relation we just sort of proved earlier on. If you sort of conjugate by an element, sort of lift of Frobenius in some sense, it will somehow just the same as be multiplying this monodromy operator N by some scalar. So this correspondence is given as follows. So it sends rho over here to, as before, the monodromy operator N is just 1 over N. So log of this for M sufficiently large. Okay? For M sufficiently large, so this thing becomes unipotent as we proved, and N is the log of that. Whereas the representation R, maybe I'll do this in a more explicit way. So if I see, so every element in the Wei group can be written as some power of a lift or fixed list of can be written as a product of a fixed power of a fixed lift of Frobenius and something in the inertia subgroup. So I can write it as sort of an arbitrary element can be written as Frobenius lift to the 8th power times some x, where I guess x belongs to the inertia subgroup. So this will be given by essentially sort of the same thing as rho, except I want to modify it by something about this N here. So this becomes this here. Oh, and also A. So this R will be somehow the original representation modified by this exponential of this nilpotent operator. The upshot is that the reason we do this is that after let's say A equals 0. Okay, let's say I don't have the Frobenius part. After I do this, then the rho of ik will be finite. That's because somehow the infinite part of this rho is already contained in this exponential part, which somehow already captures by this monodromy operator. If I sort of multiply with the inverse of that, it will kill sort of the infinite part, and then I'm left with some sort of finite part. So that's why I can take the coefficient to be C as opposed to QL. I don't somehow the L-adic sort of infinite part is already taken out by the L-adic infinite part is already taken out by this monodromy operator N. That's the upshot of this. Okay. Are there any questions about this? I know it's so that's the Jordan commission. Oh, so so this is I don't know how to write this up. So because it's Z, I want to pick something that corresponds to 1. So that's the Frobenius. Yeah, and then lift it over here. That's the future. Questions? I mean, if you have any questions, you can interrupt me anytime. Okay. So all I want to convey is that somehow this Grothendieck monodromy theorem gives a way to go from L-like representation to something sort of finite that's somewhat independent of L. as I explained somehow, when I do this, this image of the inertial group is finite, so therefore I can replace by the C coefficient. Otherwise, if the image is infinite, somehow if I have a C representation of profinite group, the image must be finite. So you really need this to happen so that you can replace the image, or replace the coefficient of the representation to be C, as opposed to sort of Q out. So maybe I'll just sort of give a quick proof of that. After you multiply with this factor, this is still a representation, in the sense that when you have phi tilde A times, say, phi tilde B, y equals to phi tilde. Let me just ignore the K here. Phi tilde A plus B times phi tilde minus B x phi tilde B times y. Okay? So when you have sort of two things multiplied together, I need to check. When I apply R to that, I somehow get R of this times R of this equals R of this, right? So on the one hand, I need to check the R. Let me just write it out. So R of the left-hand side will be exponential. So this is R of the left-hand side. By definition, I have the original representation rho times something from the unipotent operator, so the nilpotent operator n. I want to check that whether that's the same as rho of sort of the same thing. So this part doesn't change, but somehow the part I need to multiply it with is this exponential part. So I have the exponential part of minus TCL times. Now both of these belong to IK, so I put all of them in here. So P tilde minus B x P tilde B y, and what else? N, right? So I want to check that. After I made this multiplication, usually when you have a representation, you multiply with something. It's somehow. It's not, if you multiply with some sort of matrix, it's not a representation in the sense that you need to check that R of this times R of that is R of this. Now let's sort of start to sort of cancel out some terms. So rho is a representation. So if I cancel that with this, and I will somehow get I want to get rid of this part. Divide this over to this side. So I already have this part. So I just have phi tilde B y inverse exponential. So I can, let's say, divide this over. I'll be done in a minute. I'll divide this over to here, and now. Remember, this is the CL is a homomorphism, so I can separate it in two parts. P to the minus times n. Well, inside of that, y. Okay. So I move this row over to the other side, and I get the inverse here, and I basically copy everything else. Except over here, T zeta L is a homomorphism. I separate it into two terms. Now, of course, this term kill with this term. That's for sure. Now I want to compare this with this. So that's precisely the property we had earlier. Namely, when you do this exponential, so this part is the same as exponential of times this thing would conjugate on this n. So this will be rho of this tilde B y and rho of y. Minus this one. Right? So this conjugation can be conjugated onto the exponentials think about how matrix multiplies. And this bit here is precisely, so this bit here is precisely sort of q to the b times n by how the Galois group acts on the monodromy operator n. Whereas over here, this is q to the b times x, x to the q to the b, by how the, maybe still you have to need it with this. Together, this is q to the b times t to the cl x. By how the Frobenius acts by conjugation on the 10 group, so raising to b's power. So these two kind of agrees. Therefore, you have this ecology. Okay, I'll stop here. Let's take a break for 10 minutes. It's a couple of corrections. So first of all, I should have a L bar here, or maybe algebra closure of L here, so that somehow the C would correspond to L bar here. And also as well, sorry, because the matrix is C now. Apologize for that. And also L bar here as well. I realize that there's a better way to describe this. Describe the substance. Those weight representation that come from a Galois representation. All you need are the Frobenius eigenvalues. Our L-ladder units. So maybe a bad example is that if the Frobenius, say, goes to L and 1, say. So this is a very well defined representation of weight group, because for the weight groups, the Frobenius part is Z for discrete topology, so it can go whatever you want. But whereas for Galois group, the Frobenius part is Z hat, so this has to kind of converge, but in L-like topology, it doesn't converge. So this is bad. This doesn't serve. Such representation does not serve. Such arithmetic representation doesn't come from representation of a Galois group. Okay. Okay. So now I'll spend a little bit of time to talk about higher ramification group. I'll basically just sort of list all the known results in some sense. So again, K is going to be a finite extension of QP or FPP. I'll take L over K for now, a Galois, finite Galois, finite Galois extension. In the residue field, extension is L over K. Somehow L is used in two different ways for elements and the field. But anyways, so I wanna just over here normalize the uniform the valuation. I want to write VL such that its evaluation on the bar pi L, the uniformizer of L, is 1. Now I define the higher ramification group. This is something you should have already seen. So I'll go a little bit faster here. So I'm going to define the lower numbered ramification group to be all the elements G in the Galois group, such that if you apply to an element in the random integers in L, it doesn't sort of move as much. So the valuation of the difference is at least U plus 1. Well, maybe I should also say a couple of words. So it's enough to check this, to test this on a generator. I mean, in the case we considered here, OL is always okay. Start joining one element, maybe not U, but sort of maybe alpha. So enough to check this for this generator alpha. You don't have to check for every element. And also I want to make a remark that because the valuation is always an integer, so this is always the same as the ceiling of this u. Because if you are greater than or equal to u, then you must be greater than or equal to the ceiling of this u. So this is let me just write it over here. This defines a decreasing filtration on the Galois group. So first of all, this if u is -1, of course, valuation of something is greater than or equal to 0 because everything is integral. Then that's the entire Galois group. And the initial subgroup is GL over K0. And then the well inertia is GL over K1. But then you have further subgroups. Let me sort of quickly mention that. We've already discussed that this quotient here is a Galois group with residue field. Whereas the quotient here, this is the quotient of ZP at 1. And what we want to understand now are the subquotients here. Since you probably have already seen some of these, so let me just give a. So let's see. Let's maybe discuss this just very briefly. So, graded piece of this subquotient here has the following description. One. Okay. So there's an embedding of this thing into L cross. Sending, to start with an element G here in this Galois group. And I look at how G acts on the uniformizer of L. That still has valuation 1. I can divide by valuation 1. And I, of course, modulo the, I guess, maximum ideal of L. So this whole thing belongs to L cross. Okay? And you can check that, you probably have done this exercise in number 31, that if your element belongs to this GLK1, the valuation of G applied to the uniformizer minus uniformizer is greater than or equal to 2. So therefore, this difference will be 1 plus, it will be something like 1 plus uniformizer. That will be trivial in L cross, when you modulo uniformizer. So therefore, this is injection over here. In particular, that somehow shows that this Galois group will be some sort of will be embedded into the group of Russell unities, and therefore a quotient of that. In a similar way, for n greater than or equal to 1, I can do sort of the same thing. The graded piece of the Galois group, namely n plus 1, this will be embedded into. Well, let me write out what I want to do first. Again, I want to do G goes to G bar pi over bar pi. Okay? But now, this thing, we know this thing already belongs to 1 plus, let's see, bar pi L to the, I mean, when it's 0, it's just no condition. So maybe already here, this is n. Oh well. So this element already belongs here. Now I wanted to go to look at it modulo the next power. Right. So if the image goes to the next power, then the Galois group, like the element of the Galois group will go to the next filtration, basically. And I want to say this is canonically isomorphic to, just think of this as some sort of symbol, var pi L to the end. This doesn't play any role because I already reduced mod P. So, but I want it to be canonical so that it doesn't depend on the choice of the uniformizer. There's dependence on the uniformizer if I don't have this one. Or maybe I just write. This is L. But this item will depend on the choice of the uniformizer. The first one does not. Okay. Right. And maybe I want to point out this is a P group. Oh, maybe I should first of all say that these are all homomorphisms. This is all injective. So I checked with Yuan Ding, and he said somehow you already seen all these in number theory 1. I'm not going to leave an exercise. This somehow, if you haven't done this, you should do an exercise to show that this does not depend on choice of uniformizer, and these are homomorphisms, and such and such. I just only point out that this is a, this as a group, this is Z mod PZ to some power, right? So this is a P group, and it's a abelian P group. And that means that all these sub-quotients we have over here, these are all sort of, these are all abelian P groups. So therefore, the whole wild inertia is a P group, and it's a solvable group. As also P groups are solvable anyway. So, but we have a more sort of canonical filtration of this. Sorry. Okay. And also, maybe I should also say that each of these graded P's are actually killed by P. It's an elementary abelian group killed by P. So here's a key fact. That's a kind of a key property of this story. This is so-called lower numbering verification filtration. The name. Lower numbering verification filtration. As the name would suggest, later on we're going to consider upper numbering lowering verification filtration. We'll do that in a minute, but let's first of all review why we need that. So suppose that I have a situation that I have sort of a tower of extensions, L over F over K. Then, if I look at, this is a subgroup, GL over F of GL over L over K. Then, the ramification filtration on the subgroup is induced by the ramification filtration of L over K by just simple intersection. So that's good. The reason is basically it goes through the definition, because what this means is that if you have an element in L, you hit it with an element G, but this basically says Gx minus x evaluation which is greater or equal to U plus B, right? And this property is somehow, this is sort of defined by the same property. So it's tautological that this is equality, because they are defined by the same condition. Here's a big but. But if you want to look at sort of bottom part, say this is also Galois. Yes, this is also Galois. But you want to understand this compared to the Galois, this whole Galois ramification, the lower numbering ramification filtration for the big Galois group versus the quotient group. This is are not directly related. Okay, you can't pass somehow this filtration is good when you pass through subgroups, but it's not very good to pass through quotient groups. And in fact, this is bad because guess you can't have a filtration that works for both subgroup and quotient group. But somehow, it's better to have the one that works for the quotient. Because when you pass the inverse limit to the whole Galois group, you're taking sort of an inverse limit with respect to the quotient maps. So you want your replication filtration to be compatible with the quotient map, not the sum. So here's the fix for this. For L over K above, if you first time see it, it's a little bit ad hoc. I had the same feeling as well. Let's define the so-called Herbrand function. To be honest, I have no intuition of why this is the correct definition in some sense. But somehow it turns out to be the correct one. So I want to consider the following functions, phi L over K of U. The best way to write, the most sort of efficient way to write it is to write it as an integration of dt of the index of your group inside the initial subgroup. Let me finish with the definition now. Give an example. Okay. So it's just what it is. I have no intuition why they defined it this way, but nonetheless, what can we see by just looking at it? Yeah, okay. So first of all, this, as I said, somehow the lower number ramification filtration is sort of, if you have t here, that's the same as ceiling of t. So that means that this is a piecewise linear because it only changes when the t, so this function we have over here is a piecewise linear function because it only changes value when t becomes, moves to the next integer value. So this is a piecewise linear. So the function, it's called integrand, right? I'm not so sure about this English word, but anyway. The thing that you're integrating is continuous. Oh, actually, you know what? I don't need this. I want to look at the function phi. So this phi all over k is piecewise linear. The thing you're integrating is a step function. And this is, after you integrate, it's a piecewise linear function. It's strictly increasing. Maybe I say I only consider in the case when u is greater than or equal to -1, and it's concave. This is not very important. Okay. So because it's strictly increasing, so I can take. In fact, it goes to infinity, so I can take this to be the inverse. At this moment, it's completely abstract and define that the upper number filtration, V, is the corresponding lower one when you apply psi. Or, I mean, because it's an inverse function, so you can think of this as sort of, if I know that the lower number ramification filtration is at U, over here I have phi. So same thing. Okay. Okay. Enough abstraction. So let's do an example. Just to give you some sense of what's going on here, I guess. What is that integration? So let's do the cyclotomic extension QP. So my L is have this cyclotomic extension, we know that as far as Galois group is concerned, this is a trivial, right? I mean, I write the corresponding Galois group. Okay, this is a trivial Galois group. This is what do I have here? I have here 1 plus p squared zp modulo 1 plus p to the n zp. That's the corresponding Galois group. And over here I have 1 plus p zp modulo 1 plus p n zp. Right? And over here I have the z mod p to the n z cross. Right? So this is the tower of fields. This is the tower of the corresponding Galois group. Right? And I want to see sort of for which number so I want to see this is equal to g of lower what and upper what. That's what we're trying to figure out. Let's see. So first of all, this entire Galois group is g of, so this is totally ramified. So this is g negative 1 and g 0. Right? Because it's totally ramified. Let's see. Right. So let's figure out first of all the lower number infiltration and then do the upper number infiltration. Okay, what is so what is, for example, 1 plus p? Go. So if I have some sort of g, let's write g1 plus p, meaning that it corresponds to 1 plus p in the Galois group. It will act on the generator zeta p to the n, right? And minus zeta p to the n. And what do I get? I get zeta p to the n plus 1 plus p minus zeta p to the n. Right? If I have this element which corresponds to the Galois group, 1 plus p in this Galois group, if I apply to the element zeta p to the n, and I minus that, I get this. I get zeta p to the n to the p minus 1. And now if I take the valuation of this, well, this is zeta p to the n minus 1. Now, let's say n is big enough. I mean, I just want to say n is bigger than 3, just in case, just for sake. Okay? So what's that valuation? That valuation looks, I mean, like so BL of zeta p to the n minus 1, this is 1. Because zeta p to the n minus 1 is uniformizer. Now I'm somehow raising it to the pth power. So I'm just blanked. You should know it right away. So this is just p. I think it was p. Because this is sort of to the pth power. So this, how should I do it? I mean, like, think this is, I mean, write this as x, right? And this is sort of 1 plus x to the pth power minus 1. So p is very large, and the x to the p is the one that gives you the uniform, it gives you the valuation, so that's p. So because this difference is p, that means that, so this group is actually g1 equals to g2. So this 1 plus p will belong to all this g1, g2, all the way to gp minus 1. But not gp, because this valuation is precisely p. If you want it to belong to gp, you have to go, I mean, you have to have this to be greater than or equal to p plus 1. That's the definition. And now, if you have an element in here, you can sort of do the same element. If you have g corresponding to 1 plus p squared of zeta p to the n minus zeta p to the n. If you do the same calculation, you will get to zeta p to the n of zeta p to the n p squared minus 1. So that's p squared. What that means is that this generator 1 plus p squared will belong to gp and gp plus 1 and all the way to gp squared minus 1. And it will not belong to the sort of the so this 1 plus p squared will not belong to gp squared. So gp squared will be kind of here. Will not contain this element. So lower number infiltration, you can kind of already see the pattern. It just has to be g cubed minus 1. Or maybe fine, just in case I don't write something wrong. Okay, so that's the lower numbering verification filtration that you see just by looking at how this acts on the generator. Questions or comment? You look very... All you need to do is somehow start with the element here and then compute how it acts on the generator. And then takes the difference and look at the valuation. And that tells you which group this belongs to. Now I want to turn this into the upper number verification filtration. From 0 to -1 is always a straight line of slope 1. That's because in this integration, when this t is less than 0, it will go up to the ceiling, so therefore this is always 1. And after that, we see that from 0 and 1 onwards, so as it goes past 0, the group, this lower number verification, so this group here, as you t bigger than 0, this will become this subgroup here. Okay? When t is bigger than 0, the subgroup will be 1 plus p, zp, inside this group here. So index is p minus 1. So therefore, starting from 0, this integration of a step function, right? So you're going to be integrating a step function, which takes value 1 over p minus 1. So this thing has slope 1 over p minus 1. And how far does it go? Well, you go to p minus 1. That's this. This is good enough. So let's say this is p minus 1. Okay? And starting when t gets to p minus 1, if you want to keep going, this group becomes smaller, like here. When you pass, the moment you pass p minus 1, becomes this group here. So this group has index p times p minus 1 inside a bigger group. So now your slope becomes smaller. Slope 1 over p minus 1. So when it reaches to the point where p squared minus 1. And after passing that, the slope, you can see that slope is just 1 over p squared p minus 1. And continue. And what are the sort of the y coordinate? Because it's p minus 1, the slope is 1 over p minus 1, so this is 1. And between these two, the distance is p squared minus p, right? And the slope is precisely 1 over that, so this point is precisely 2. And you can kind of imagine what's happening next. So therefore, you see that this is g upper 0, this is g upper 1, this is g upper 2. So that's the upper number ring filtration, verification filtration. I mean, this is sort of just give you a sense of what it looks like. And for a Abelian extension like so, these numbers are always sort of as nice as this for loop integers. We'll see that later. So these are just basically, 1, 2, 3, 4, and so on and so forth. Any questions about this? Good. So here's a key theorem of why we want to. I'm not going to prove this, but just sort of take it as a fact. So if I have L over F over K, all Galois, finite Galois extensions, then the image, so this upper number filtration is compatible with quotient. The image of V so the image of this upper number ramification filtration for this one, in the quotient, is precisely the same thing with same index b. I.e., the Galois group of the ramification filtration for the quotient one is precisely the big one. Times the, that's basically the image of this inside the quotient. Here's a corollary. Now I want to, for b greater than or equal to -1, I want to define GKB with inverse limit of this. So because this ramification filtration is work compatible with quotients, so I can really take inverse limit of this to the full Galois group. Then T over KB is just this. So I can just sort of take it in the absolute Galois group. And then for any finite extensions, the ramification filtration will be just induced by this sort of ramification filtration on the absolute Galois group. For a technical reason, I want to also define GKB plus to be just union of all the numbers that's bigger than b of GKW. But when you take this union, this may not be closed. You have to take a closure. Okay, so this is a closure. So now I can define it's called Artin Swan conductor. For a representation rho GLB, or maybe I can define it for the Wei group as well, such that the image of the inertial subgroup is finite. For example, if V has coefficient C, that's not a problem. And also I guess the characteristic, and somehow this V is over a field of characteristic 0. Then I can define the Artin conductor of this rho to be, I'm going to write it in a very fancy way, but somehow it's not bad. It's the dimension of the part that's there and under. It's this thing. Basically, if you let V to change from 0 to infinity, at some point the dimension of V fixed by this subgroup changes. At the moment it changes, you take the dimension changes, and then it's weighted by the corresponding V, and take the sum of that. And this is when, so this is when V is greater than or equal to 0. Swan conductor is a little bit different. So you take all the V greater than or equal to 1, but take V minus 1 of the sort of same dimension. So there are two conductors, arcing and swung conductor. We're mostly using the first one, arcing conductor, in this, for what I'm about to talk about, I guess, for an arcing conductor, but not quite a swung conductor. The basic difference is that somehow arcing conductor of rho is the same as arcing conductor of rho restricted to an unramified extension, the Galois group of K unramified. But then swung conductor behaves well under the tamely ramified extension. So namely, if you have a K prime over K, tame, then the corresponding swung conductor will be sort of just simply multiplied by the ramification degree up to restrict to the tamely ramified extension. So swung conductor works better with tamely ramified extension. Arcing conductor works better with unramified extensions. These two are not too much different in some sense. But we'll, like in our lecture, we'll probably just use just a little bit of arcing conductor. So let me quickly mention Hasse arcs, which basically says that the arcing conductor and swung conductor are integers, always. A corollary of this is that if you have a sort of a cyclic extension, okay, then you can right, and then you can consider a chi of so if you have a cyclic extension, then you can look at sort of the Galois group. Maybe V1, maybe call it V1, and or maybe you don't have, it's just a Billing extension is fine. Then you can find the ramification filtration labeled by upper numbers, as so. But you want to pick out the part where this actually representation suddenly jump. Anyway, this is sort of how should I put this? So this is inside. This is basically where as B goes from small to large, this is where things jumps. Then you can take a representation, sort of chi bi of the quotient. That doesn't factor through. A quotient by sort of the next, the bigger subgroup. So bi, let's see, bi minus 1. Okay. So if you have some sort of filtration, this is a Billing extension, right? The quotient is some abelian group. You can always take a character of this that doesn't factor through the quotient by the larger group. Then the arcing conductor of this bi is precisely just this bi, because by how it was defined, the place where it jumps is precisely that bi, and that's a one-dimensional space. You pick out the bi here, and the Hasse-Arp theorem says that this bi are integers for everybody. These bi's are integers, and therefore, I guess it tells you that for any abelian extension, the places where these ramification break, they jump, are integers. So, I guess that's usually when people say Hasse-Arp theorem. That's usually the theorem that says for abelian extensions, the jump, sort of this ramification jumps are integers. But there's a more, I guess, I stated in a more general form that all the representation has arcing and swung conductor being integers. I guess somehow these are kind of the version I saw was to prove the abelian case first and then to use the general case. But maybe there's a more direct way as well. Anyways. Are there any questions about these? So that's everything I want to say about sort of higher ramification theory, I guess. Okay, good. But only 10 minutes. Well, let's see how far you can go. I'll now review the local class field theory. I want to take K to be a local field as before. So first of all, I only want to state the sort of the theorem sentence. So I'm not going to prove it, of course. So I want to start with the local class field theory. The first statement is reciprocity map. How should I put this? I think of this local class field theory as an isomorphism called arcing reciprocity map between the abelianization of the weight group with K cross. So this is the abelianization of the weight group. And of course, this sits inside. There's a natural map to the abelianization of the Galois group as well. The usual state mu C is that the sort of the pro-finite completion of the K cross is isomorphic to the maximum sort of abelianization of the Galois group of K. And the way I normalize things is that the uniformizer here goes to the geometric properties. Okay. And recall that when I write this K cross hat, I really mean bar pi to Z hat cross OK cross. Okay? So you have the units part, and the uniformizer part I raise to Z power, but then because of the pro-finite completion, I have the Z hat part. And of course, this is just sort of bar pi K to the Z cross OK cross. And this is sort of what the embedding looks like on this side. And the weight groups I somehow have that. And inside of this, I have the units in K cross that correspond to the inertial subgroup of the maximal abelian extension of K. Okay. So you should think of sort of K as all the maximal unified extensions abelian, and then K abelian, and somehow this is the inertial subgroup. Okay. So the reason I spend this time to talk about the ramification filtration is the following. So inside of this, I have var pi k to the I, OK. Okay. This is congruent subgroup. So this would correspond to the, I should write G. But then I is greater than equal to 1. The sort of upper numbering ramification filtration, this index I will correspond to the congruent subgroup we have over here under the class field theory. I mean, of course, this is equal to GKI times GK comma GK. That over, I made a mistake. I should have done that. But anyways. That's okay. This is bad. Okay? So that's something we get from class field theory. part 2. So that's for one field, how I think of class field theory, just to use that. So if I have a finite extension, then I have L. And I have K here. Okay? So the question, how do these two relate? Well, first of all, the weight group of L would naturally map to weight group of K. Basically, the Galois group, you can think of the Galois group of L as a subgroup of Galois group of K. So therefore, you have a map this way. So there's a natural map. What this corresponds to on this side is a norm map. Okay? I'm saying this is a diagonal commute. But of course, we have the natural inclusion this way. So somehow we have a corresponding map on this side as well. It's called a transfer map. Let's sort of define this. So it says that if H is subgroup of G of finite index, then there's a natural map from H abelian to G abelian. The way I didn't write down an explicit formula. The reason is that the best way to understand this. Oh, excuse me, I wrote the wrong way. So from the bigger group to the smaller group, GAB to H. The best way to see how this is defined is to realize that the G abelianization as the first homology of G with coefficient Z, H abelian as the first homology of H with coefficient Z, and this is just simply the restriction map. So this is what homology group gives you. You can reinterpret in terms of cosets if you want to. I'm not going to do that. Just sort of review of what these things are. 3. If tau is in a Galois group of Q, so this is restricted to the case of QP, I guess. Then I'll have this arcing map as so, right? So now I have a big Galois group action. Then if an element in here, alpha, I can apply tau to this alpha. Now this no longer belongs to K anymore. It's in tau of K. So this is the same as tau of arching map K of alpha of tau inverse. Namely, this belongs to a weight group of abelianization of weight group of K. And when you conjugate by this, now this belongs to a weight group of tau K abelian. Namely, you can first of all act on this element and then do the arcing map. Or you can do the arcing map, get to the Galois group, a weight group, excuse me, and then you conjugate by tau. So that you get the same result. Maybe just quickly write down what local. And you're going to see a lot of sort of undefined things here. But I want to sort of give you some sort of quick, maybe not local one. Maybe I don't have time for that. Let me just sort of do another case. Sorry about that. So I want to also talk about the case when K equals R, where of course Galois group is element 2 elements. but I can still define. Sorry, please allow me to finish. So when this, with K is R, the weight group is this one. So remember that you always have a map from weight group to the gamma group. That's just sending the projection to the 1 and J. But then the weight group of R has this additional part C, where Y and J acts by sort of conjugation. Okay? For me, I think somehow these two are, and so I have something to check. Just to double check that whether things are sort of compatible or not. So I have, let's see, maybe write it over here. Oh, let me just write down the. In addition, the weight group of this one, you can check. This is sort of isomorphic to positive part. So I don't have time. Maybe you can check after class somehow. This is a diagram that looks very much like a QP case. I'll stop here. Sorry for running over time. Somehow the upshot of this optimization looks like so. And then somehow this arcing map goes like this, taking the absolute value, and then this will tell you the sign of everything. And the whole diagram commutes.